assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
Hi there. So for this problem, we need to calculate first the potential at the center of this circle and later at a point P that is at a distance D from the center. So the first thing that we need to know when we have a uniformly distributed charge, in this case it is in the form of a circle, and we have the quarter of this circle has a charge Q1 and the rest of it has a charge Q2. So to determine first A, the potential BC at the center of this circle, we need to take into account, the first thing that we are going to do is to take a differential of charge that we call the dq. And we know that this differential of charge will produce a potential that is given by the following formula. The differential in potential is equal to the differential in charge over 4 pi epsilon 0, the distance to that point. In this case, because we are in the center of the circle, every differential is at the same distance r, which corresponds in this case to the radius of this circle. So having that, we can define this differential dq as the density, linear density times the radius times the differential in angle. So with that in mind, we can simply just take the integral of this differential in charge, and this will give us, well, we're gonna try first with this segment in here, and that segment in here has a positive charge. We're going to call then density a positive density, and it also is not in all of the circle. It is just on 1/4 of this circle. So we're going to see this right away. In this case, when we are integrating, the density do not depend on the angle, so we can take it out of the integral, and so we are only to integrate the differential in the angle. So in this case, the integral of the charge is the charge, and the charge in this case is Q. We're going to call this Q, simply Q, and it is Q1, but we are calling just Q, and it is the entirely charge of this segment, and this is equal to the density, the linear density R, and we can see that when we take the integral in the differential of angle, we are going to sum all of these contributions. So it is this angle in here, and 1/4 of a circle is just 2 pi, because 2 pi is the angle of the entire circle, but we want 1/4 of it, so it's 2 pi over 4, and we can simplify this further to pi over 2. So this is the charge for this segment, and we can solve for lambda positive, so we will have 2 times q over pr. So This is for the positive segment of this circular charge or circular uniformly distributed charge. Now, similarly, like this, we can obtain for the negative segment. So in this case, when we take the integral of this differential dq, we are going to obtain minus 6q, because that's what we are given in here, that q2 or the negative part of this segment is minus 6q1. That we are just going to call it minus 6q. And in this sense, we will have the same for the other part. We're going to call this minus the minus density times r, and the angle. In this case, and the angle is the rest of the circle. So we can obtain this subtracting to 2 pi the other segment, and that we just have obtained, it is pi over 2. So we will obtain, it's easy to see that we will obtain 3 pi over 2. And we can see that if we sum this angle with the one in the other, in the previous one, we will obtain 2 pi, which corresponds to the circumference of a circle. And solving also for the and then linear density, we will have 2q 12, because this is sets in here, so it's minus 12q over 3 pi r. We can simplify this further as minus 4q pi r. So this is for the negative segment. So with this set, we can see that the differential in the potential is equal to the one created by the positive charge plus the one created by the negative charge. And in this sense, when we integrate this, we are going to obtain the following. Oh, let me just write in here for the differential, how we obtain it, what we obtain from here. So in here we obtain this for the differential in charge for pi epsilon 0 r plus the negative r and when we integrate this, we are going to obtain the result that we just have obtained. So we will have the value for lambda, which is 2q for the positive part, this in here, this, and it is 2q pi over r. Also the angle, because we integrate in the angle, so this is 2 pi and pi over 2, and the other segment, that this is this term in here, so it's 1 over 4 pi epsilon 0 r. And the negative part, which is sum of that, well, in this case, is negative, so we're going to put it here, negative. And that is 3q over 2 pi r epsilon 0. And if we, okay, so, no, sorry, this is not the result in here. We obtain that from Negative lambda is this value in here. So we're going to put that in there. 4q over pi r. And the angle that this segment described is 3 pi over 2. And the term, this term in here. So this is it. This is all we have. Now, having this, we can simplify this. Oh, in here, you just don't need to like include this because it is already included in this part, so it's not in here. So we can see that we can simplify something here. We can go this with this, this with this, and also in here we will have this with this, and all this with this. So after we subtract these two terms, we are going to obtain minus 5q over 4 pi r epsilon 0. So this is the potential at the center of the circle. We can simply substitute all of these values. Q, as I said in the beginning, is just Q1, which is 4.20 times 10 to the minus 12, because that's the picocoulomb is 10 to the minus 12 coulomb. And we also have in here 4 pi. The radius of the circle in this case is 8.20 centimeters, but we can convert that to meters because we need it in that. So it is 8.20 times 10 to the minus 2 meters. And when we put that in here, and we also need the value for epsilon 0. So let me search for it. 8.85 times 10 to the minus 12 farads per meter to the minus 1. So when we put all of this into the calculator, we obtain a value of minus 2.3 volts. So this is the electric potential at the center of the circle. And part B of this problem asks for the potential of the point P. We can see in the figure that the point P is in the vertical axis, but away a distance of 6.71 centimeters. We can also transform this into meters. So it is this value. So the only thing that it changes is the distance of every differential charge to that point. And we can see this easily from the picture. It will be this distance in here. And this distance in here can be just calculated as the hypotenuse. So we can see that it should be d squared plus r squared, because it is this distance in here, the square root of all of this sum. So we just simply gonna substitute this value in here. So I'm gonna say like the distance in this case is the square root of r squared, which is the radius of the circle, plus the distance to the point P where we want to calculate the electric potential. So it's d squared. So with this, we just simply need to substitute this distance in the expression that we just have obtained previously. We just need to change the value of the distance arc. So it will be something like this: minus q phi q over 4 pi, the square root of r squared plus d squared, and this time epsilon sub 0. So we just simply need to substitute again all of these values. So we know that the charge is 4.20 times 10 to the minus 12 coulomb over 4 pi. The distance in here should be like the radius square, so it is 8.20 times 10 to the minus 2 meters square plus the distance d to the point P, which is 6.71 times 10 to the minus 2 meters square, and we take the square root of all of this, this square, and also the value of epsilon sub 0. I'm going to put it right in here. It is in the denominator, so we will just multiply this by this, and that is 8.85 times 10 to the minus 12. So putting all of this into the calculator, we obtain minus 1.78 volts. And this is the electric potential at the point P. We can see that this result is correct because the value is less than the one we obtained before, and it should be because we are far away from the circle, the uniform charge circle, so it should be less. This is it for this problem. Thank you.